have probably the PowerPoints there also. I want to see that I got it there and that you can open it up. Is it in your period for fourth term? Do I need to hide third term? You have chapter 6,
Yeah,
like all the stuff there? Okay. The assignment list might be an important one to make sure opens. I'll try and do that for the next chapter also. Since now we've got a lot of activities and some of you will be gone a day, or you have games a day, I'll try and put that list up there for the chapters so that you can, like you're going to be gone Wednesday, maybe you can do the assignment ahead so you know what you're missing and I guess schedule your time a little bit better as far as when you have time to work on something. So that's what's there. And then if you click into one of those like PowerPoint things, that should be pretty much the presentation that I'm going through. So if you need to look there for some examples or some notes. So I'll try and do that for the next chapter also, to show you, to give you that. And remember, you can go to the videos. If it's not a current YouTube video that I recorded, if you go down far enough, you'll find the ones that were recorded like last time that I went through that lesson. So you should be able to catch up if you're going on something. Otherwise, you've got your book to look at, and most of you are good enough about figuring it out on your own. You probably can do a lot of that if you're missing. Okay? So just some things this time of the year we kind of need to allow for all these activities that you're going to be going to, possibly just a little early or something like that at times. All right, so today we're going to try and get done here in about a half hour, so you have time to get that quiz in that you didn't get done on Friday. So I probably cut out a few of our things that I typically would do to make sure that we get done in time. A kite is the first shape, and you're on lesson 6.6. Definitions are not in your notes, so you need to add some definitions. So the first shape is a kite. A kite is a quadrilateral with exactly 2 pair of congruent consecutive sides. And notice how that reads. It doesn't say opposite sides congruent. It says consecutive sides. And it's not all consecutive sides, because if you had all consecutive sides congruent, all sides would be congruent, and that would end up being a rhombus. So a kite has exactly 2 pair of congruent consecutive sides. So 1 pair on the left of my picture, and then the other pair on the right of the picture. It says a kite has 1 line of symmetry. If we notice that line of symmetry, there's a lot of things that we can figure out about the kite. So what segment, what diagonal would be the line of symmetry on this one?
A to C.
AC, correct. So this would be my line of symmetry diagonal. So think about folding it. Besides the sides that I have marked, what else would we be able to determine are congruent? Angles, which angles? DAC and BAC are congruent. So in other words, this diagonal bisects that angle, correct? And same thing on the other end, right? So that one's bisected. Would angle B and angle D match up? Congruent? And we could even maybe convince you that based on third angles theorem or congruent triangles and CPC/TC, things like that. So we do get those 2 congruent. How about the total angle A? Like angle BAD, is that going to be congruent to BCD? Is angle A, the total, the same as angle C? That might be one thing that we'll need to clarify, because just by folding it, we can't be sure that it does. If you fold it the other way, like if I would fold this, notice our sides wouldn't match up, and so in that case our angles wouldn't, but maybe it's just out there further. So we're going to try a little bit of drawing construction and see if those angles are the same. So the next thing, rather than going right to the theorem, I want you to grab the compass and straight edge and have you construct a kite. So we can try a little measuring. You might just have to go to the back of that paper. So some of you grab things, others would not. The construction, you might notice, is made up of 2 circles. Different size circles, it says. So you need to select 2 points. Those are going to be the center points of your circles. So on your paper, put 2 dots, maybe a couple inches apart. Do they have to be directly horizontal? No, they don't have to. And do they have to be a specific length apart? No. You're just making a random kite right now. But put those 2 points, those are 2 corners of your kite. Then make a circle with one of those points as its center. I don't care exactly how big, but don't go too big. You don't want it to be past the center point of the other circle. So keep the circles between the 2 centers. So draw 1 circle here. Then when you go to the center for the other circle, you have to make the second circle either bigger or smaller. Either bigger or smaller for the second circle. You want it a size so that the 2 circles intersect in the space between the 2 centers. Okay, now the other 2 corners of your kite are where the 2 circles intersect. So your kite is made out of the 2 centers and the 2 intersection points. Connect nicely with your straight edge.
What?
That's what
Oh.
where they cross. You just kind of went to a random point. Okay. Now, why is that a kite? Well, what's the segment called that goes from the center of a circle to a point on the circle? Radius. So for this left-hand circle, isn't this segment a radius? And this one also a radius? Does the radius change in a circle? No. So those 2 lengths are the same. And for my right-hand circle, this radius is the same length as that radius. So you do have a kite. So what would happen if your 2 circles were the same size? Those would all be the same, so it'd be a rhombus. So that's one way you can construct a rhombus, just 2 circles that are the same size. Okay, so what were we not sure of? We weren't sure if there were some angles congruent. So got a protractor. Some of the packets have protractors, not all of them. Anyone without a protractor? This one has a protractor. This one, Thomas. Have to try and round up a few more protractors. All right, so measure the angles. And we were thinking that there would be 1 pair of opposite angles congruent because of a line of symmetry we were thinking through. So you should have 1 pair that are congruent, and then we weren't sure about the others. If they were congruent or not. What should all four angles total? 60, correct. Does that mean two of them always have to add up to 180? Well, that only happens if there's parallels. Are there parallels on your kite? I don't think so. Some of them look kind of parallelish. If your circles were close to the same size, if you've got something that's really close to a rhombus, they're probably going to look parallel. But some of your kites are really stretched out, skinny, and so it's a little bit more obvious there are not parallels. Okay, so we had one pair of angles congruent. Were the other two congruent? No, they weren't. If you drew in the diagonal, we said that they would bisect, but they're not the same. So maybe that verifies just a little bit of what we were thinking of. Okay. All right, with your straight edge, draw in both diagonals. Are they the same length? So you're shaking your head before you even really drew them because you could tell one's a lot shorter on your picture. Again, some are probably close. Anything that might be true? Do they bisect each other? No? It looks like vertical. Oh, which ones are you talking about?
Like the diagonal from the two vertices, not those, but the ones with the angles congruent. A and C, it looks like C is.
Looks like that total A and that total C are congruent?
Yeah.
Is that what you're thinking? Or the
but
small?
I was saying like the diagonal AC, looks like it's bisected.
Looks like it's bisecting the angle?
No, it looks like DB.
Oh, it is bisected by DB? Okay. How can we verify that? Can you measure from E to A and E to C? Yeah, you could try a construction. Might be real quick that you could measure. Is that length the same as that one?
Sure.
Why are the triangles congruent? There's really a lot of ways. So what we're thinking is those two lengths Daniel's talking about should be congruent by CPCTC. Some are talking about these great big triangles being congruent, and I would agree, there's a lot of things. But notice AE is not a side of the big triangle. So you really would need to be looking at these smaller triangles. And I don't know that I have a lot. Well, here, these two, those, and the reflexive. I suppose this little triangle, we could get congruent to that little one easy. So AE and CE are congruent, maybe supported by CPCTC. Angles? Are those 90? Looks like it, or you measured it?
It is.
Sure looks.
Okay, some measured, yes, they are perpendicular. So what kind of little triangles are there? There's right triangles. What do we use to find a missing side of a right triangle? Pythagorean theorem. Some of the examples we'll get to involve that. Okay, we better move on to the actual theorem. There's two theorems related to kites. If a quadrilateral is a kite, then its diagonals are perpendicular. That was one that you just told me. And if a quadrilateral is a kite, then exactly one pair of opposite angles are congruent. And we could figure out which ones are the congruent ones if we notice where the line of symmetry is. So B and D were congruent angles, but A and C were not. examples related to kites. Anyone still need the screen? Okay, Daryl's going to make an actual kite by doubling all the measures in the pictured kite. What's the total amount of binding needed to cover the edges of this kite? He's going to make it twice as big. How much binding does he need to go around here? So it's a story problem. What am I really asking you to find? Perimeter. Yeah, the side lengths and add them all up. We do want to double the measurements. So we're going to make it twice as big. So this we're going to use as 26. This as 32. Second period we forgot to do this. 44, 32. Okay, so we've doubled everything to make it twice as big. Now let's figure out what the perimeter is. Do what? Pythagorean theorem to find the sides. Okay, girls, you do the red triangle. Guys, you do the green one. Pythagorean theorem. And let's stick with a square root answer. Let's not even simplify it. Come up with the square root of whatever. Girls, you got the square root of. I'm not worried about simplifying it. Just square root of what? 1,007?
700.
1,700. Okay, guys, square root of
2,960.
2,960. Okay, since it's symmetrical, we've got two of those, and we've got two of those. Now add up those four numbers. If you can do it in square root form, you're getting a more accurate final answer. So add up square root of 1,700 plus square root of 1,700 plus square root of 2,960 plus square root of 2,960. Do you have a calculator you'll be able to bring? On something like this, since we're going to decimal, we'll probably need the aid of a calculator. What are we getting for the perimeter?
The square root of 9,320.
Okay, wait a second. You can't add these together unless they are the same. I mean, you can't come up with the square root of something like that. Well, what? Just come out to 191.3. Okay, so do the square root of 1,700 plus square root of 1,700 plus square root of 2,960 plus square root of 2,960. Figuring out how to use your calculator to get that? Now, if you can keep it as the square root, that's going to be a more accurate answer. So I guess what I was saying is you can only add square roots if they're like terms. So you can add the square root of 3 plus the square root of 3. That's 2 square roots of 3. It's not the square root of 6. So I think, at least that's what I thought Chris was doing, was adding up those numbers. And you can't just add those, no. Okay, thumbs up or down, getting that to work? Do I need to hold off at all? Okay, so Pythagorean theorem is something we do to find missing side measurements. This one was a similar type, but we're trying to find the diagonal, let's see, this one. How would we find KL's length? I got measurements that are in the reading. 30 was this whole diagonal. Is the JM the diagonal that's cut in half, or KL? Okay, JM is the one that gets bisected. 15 and 15, right angle. Okay, to here, we have to figure that out. From there on down, we have to figure that out. And then add together from those two Pythagorean theorems. Do you understand how to do that one? Okay. Just find that length and then find the bottom one and add together. If you do, I'm going to just go on to the next kind of problem. All right, let's do an angle type. Okay, here's a diagram. It's a kite again, sides that are congruent. PQR, this whole angle is 78 degrees. TRS, this small angle is 59 degrees. We're supposed to find QRT. We're supposed to find that angle. Now, is that the one that's bisected? Where's the line of symmetry? This isn't the line of symmetry. This one's the line of symmetry. So nope, the 59 and 59 isn't correct. So what else can we do with angles? Okay, there's an angle bisector where, Toby?
Q.
Okay, angle Q is bisected. Angle RQP is bisected. So half of 78 is 39. 39. Does that help?
Yes.
Those are all right.
Okay.
Oh, so nothing.
Yeah, it's 50.
So you can do triangle sum now.
Yeah.
90 and 39 is 129. So 180 minus 129. Is that 51?
Yeah.
And let's keep going. Can we find some more? Can you find this angle?
Yeah.
How much?
180.
31.
31.
31.
59.
9.
51.
We found all of them. Now also notice this half is an isosceles triangle. So we could have taken 180 minus, what was it, 78? And then divide 102 by 2, 51, 51 for the base angles. So you could do some isosceles triangle stuff in there too. Okay? All right, so there's a little example related to the angles. We found more than what was asked, so I don't need to do the next couple examples because we did that all together there. All right, let's take a look at isosceles and trapezoid. And if we had more time, I'd have you create one, but we're going to need to just go to the definition and the theorems, I think. Okay. Trapezoid. A trapezoid, just the definition, a trapezoid is a quadrilateral. Trapezoid is a quadrilateral with exactly one pair of parallel sides. Parallelogram has two pair. Kite has no pair of parallels. Trapezoid has one pair of parallels. It's not always the bottom and the top, just depends which way it's turned. Each of the parallel sides is called a base. So base, or the bases, are the parallel sides. The non-parallel sides are legs. So the sides are either bases or legs, depending if they're the parallels or not the parallels. And there are base angles. Remember base angles in triangles? Triangle, base angles were along the same base, or along the base. Same thing here, but you've got two bases. So you have to talk about one pair at a time. So angle A and D would be base angles because they share the segment AD base. Angle B and angle C are base angles because they're at the ends of the base BC. So any angle really could be a base angle. You have to pair them upright. But angle A and B are not a pair of base angles. because they're on different bases. They're on the same leg, they're not on the same base though. So pairing up correctly. Now in generic type of trapezoid, like I've got drawn up there, there's not a whole lot that is unique about them. I mean, your diagonals are not gonna be the same length. Opposite sides are not parallel. Opposite angles are not congruent. It doesn't have any certain properties really. When it's an isosceles trapezoid, that's when it has some special properties. What did isosceles mean with triangles? Two sides, or at least two sides congruent. In a trapezoid, it does mean two sides congruent, but the two that are congruent are the legs. Are you done with this screen? Looks like. Okay. And isosceles trapezoid is where the two legs are congruent. And these are the types of trapezoids that have some properties and theorem traits to go with it. So your definition, an isosceles trapezoid is a trapezoid with the legs congruent. That says an isosceles trapezoid has one line of symmetry. Where would that line of symmetry be?
Down the midpoint.
On this
of the
one,
base.
vertically down through the middle, correct. So it depends which way it's turned. But if you think of that line of symmetry, again, a lot of the theorem ideas can be figured out. So if I have a line of symmetry here, what angles are congruent? A and B are congruent. C and D are congruent. Is there any relationship between A and D? Think about your parallels. This side can be thought of as a transversal.
Whoa.
Notice they're same side interior angles. And if these are parallel lines, then those would be supplementary. So these two have to add up to 180. B and C would add up to 180, which makes the 360 total for the quadrilateral. All right, the theorem is going to say base angles are congruent. So notice how that matches with our definitions. The other part in a theorem is about the diagonals. And again, if we had time, we'd calculate, or we would measure. But two diagonals. Do they look perpendicular? No, and if I would really stretch it out, it would be even more obvious. They're not perpendicular. Does it look like this is the midpoint, that they bisect each other? No, they don't bisect each other. So what's special about them, they're the same length. This diagonal total is the same as this diagonal total. That's what kind of keeps it symmetrical. So those theorems are summarized in these three, or those ideas are summarized in these three theorems. The first two are basically converses of each other. The first one is if you know it's an isosceles trapezoid, then the pair of base angles are congruent. The second one starts with a trapezoid that has one pair of base angles congruent. Then you can identify it as isosceles. Why they probably didn't put those together as a biconditional is on the 664. If you just have one pair of base angles congruent, it works. And the top one mentions both pair of base angles. And the last one, 665, is about the diagonals. A trapezoid is isosceles if and only if its diagonals are congruent. Notice the biconditional terminology, so it can go both ways. If it is isosceles, the diagonals are congruent. If the trapezoid has diagonals congruent, then it's isosceles. let's zip through a couple examples before we start our quiz. Okay. On this one, we've got JN is 10.6, and L is 14.8, but we're supposed to find KM. So what are some things you can use? Is it an isosceles trapezoid? Okay, yes, so then we've got some theorems. So what's it say about diagonals? They're congruent. So how long is JL? You're gonna add those together, right? 25.4 when you add. So KM then would be 25.4 also, would be the very same length. So it's not bisected, but they are the same total length. I have a different picture. Get rid of all my writing. Oh, I don't know why it went out. I guess it's saying we're done. I hit something. Okay, rather than take the time to go back, let's just call it quits there. One of those hit him. All right.
Yay.
Yay. I think I just had another one where you were trying to find the angles. I think there was one like this on it.
Our wedding.
All right, sorry about that. That's fine.
More wedding stuff.
Wait, 4:32.
Non, gone, and none.
We're gonna be on the same page again tomorrow.
Then pentagon, hexagon, heptagon, septagon, octagon, nonagon, decagon,
I don't know. Unagon, okay.
11, 12,
A
I think
monogon.
those say dodecagon.
That one.
Dodecagon, dodecagon.
No, you don't need construction tools on the case.
Are we gonna win this?
You might want a piece of graph paper possibly. On the assignment, I don't believe so. I don't think we are.
Yeah.
We'll do some constructions in class tomorrow of like a rectangle, rhombus, square.
She said you might.
Yeah, you might want some graph paper
For the quiz or
for the quiz.
I'll just cry.
or you can borrow one mine.
Here you go, Chris, take the test. Quiz thing.
Did I get enough handed out for everybody? Looks like I had a bonus on the quiz for it that would be the construction, so if you get to that bonus,